Here we see a circuit that includes operational amplifier as shown right over here, and we also see we have got two resistors and two capacitors as shown. We have got an input signal right here, and here we have an output signal. The output of the operational amplifier is tied back to the input, specifically to the negative pin. The positive pin, we have a capacitor right here, and this is a negative feedback, this is a positive feedback, because the output through this capacitor is coming back to the positive pin of the operational amplifier. So this circuit in fact acts as a low pass filter, second order active low pass filter using sallen-key topology. Here you have been given the values of the resistors 10k each, values of the capacitors 1 nanofarad each. The cutoff frequency of this type of filter is expressed as omega naught, that is equal to 1 over R times C, where R is equal to R1 is equal to R2 and C is equal to C1 is equal to C2. Because the resistors are of equal value, capacitors are of equal value, you have an expression as given by this equation. Otherwise, you can say that the cutoff frequency of this filter will be omega naught is equal to 1 over R1 into R2 into C1 into C2 if the resistance are not of equal values and capacitance are not of equal values. Now you can see that we have applied an input to this node. There is this node right over here, there is this node right over here. So at these two nodes we can apply the KCL, Kirchhoff's current law, to derive the transfer function of this circuit. A transfer function will be the ratio of output divided by input, which is expressed in terms of the impedances offered by resistors and capacitors. Now if we qualitatively and quantitatively analyze this circuit, we can see when the input signal frequency is very less than the cutoff frequency of this filter, the impedances offered by C1 and C2 are huge, making C1 and C2 acts as open circuits. So this capacitor is open, this capacitor is open, so we can look at the circuit as a simple V in is coming to the positive pin and V out, since it is tied to the negative pin, opamp is acting as a voltage buffer and V out will be equal to V in. This is the case when input signal frequency is very less than the cutoff frequency of this filter. On the other hand, when the input signal frequency is very greater than the cutoff signal frequency of the filter, impedance of the capacitor C1 and C2 are negligible, making C1 and C2 acts as a short circuit. So you can see that this capacitor is now shorted, this capacitor is now shorted. So since this capacitor is shorted, V in, which is applied right over here, the voltage that comes at the positive pin is coming to ground, and therefore The voltage at the positive pin is 0 volts and the output will also be 0 volts. So there is no output when the input signal frequency is very greater than the cutoff frequency of the filter. So clearly we see that there is a response of the filter which is something like this. So the region left to this line is called as pass band of the filter. The region right to this line is called as stop band, and this filter is acting as a low pass filter. Okay, so that's it. That is it about filter response. So hope you found this information useful. If you did so, an exercise for you would be, imagine you have C here instead of resistor R, you have C here instead of resistor R, you have R instead of capacitor C, and you have R instead of capacitor C. So here R1 is replaced by C1. Let me write here, let's say it is replaced by C1, this is replaced by C2, C1 is replaced by R1, and C2 is replaced by R2. Again, the cutoff frequency of this circuit is omega, which is equal to 1 over R times C, assuming C1 and C2 are equal value and R1 and R2 are equal value. Now with this arrangement, qualitatively and quantitatively analyze the circuit and tell what the circuit response will look like. Is it still a low pass filter or something else? Write your answer in the comment section. So till then, wish you happy learning.